Okay, welcome back for the second part of this AG-WaMED Masterclass on the SWAT model. And I leave the floor to our colleague Ismail for the second session. Thanks a lot.
Hello, everyone. My name is Ismail, a research fellow at the University of Florence. Thank you, Giulio Castelli, for giving me and for inviting me to provide and deliver this presentation. In the previous presentation, we have seen with Lorenzo how to set up the SWAT Plus model. In this presentation, I'm going to show you how to use and to perform sensitivity analysis, calibration validation process for an effective use of hydrological models, namely SWAT Plus, in simulating the hydrological behavior of a watershed. So to start, let me share my screen so everyone can observe the presentation. Okay. I have almost 45 minutes to interact with you. I have divided it into parts. The first part, I will provide you a brief overview of the sensitivity analysis, the use strategies and method in hydrological model calibration, the model calibration and related uncertainties, how to verify and validate our model, and based on which performance criteria. In the second part, we will calibrate and validate the robot watershed using robot data. The first step in calibration validation process is the sensitivity analysis, especially for spatially distributed hydrological models, which potentially involve a large number of parameters to be specified and calibrated. So the sensitivity analysis is defined as a method of identifying the most influential and important model parameters that control and impact the output variable. We distinguish generally two types of sensitivity analysis, local and global method. The sensitivity analysis allowed us to focus on sensitive parameter, which results in a better estimated parameters values and reduced uncertainty. Here are some methods widely used, sensitivity analysis method widely used to identify sensitive parameter and that are available in SWAT Plus toolbox. The model calibration is generally used to identify and estimate values from the model parameters, enable the model to closely match and fit the behavior of the real system it's represent. For hydrological model calibration, we distinguish two calibration methods are usually used, the manual calibration and the automatic calibration. For the manual calibration, involve using or adjusting manually model parameters based on repeated testing and observation until the desired performance is achieved. For this type of this method of calibration, it's time-consuming and difficult, especially if we have parameter dependence, namely if we are for non-experienced and non-specialist users. For the automatic calibration, based in using numerical optimization algorithm to automatically adjust model parameter, aiming improving the model performance and match its output, simulated output, with the observed data based on performance criteria or objective functions. This method doesn't have physical meaning. That's why the parameter value are constrained within a range, a physically realistic range from either the literature data or field measurements to provide results that are meaningful based on physical ground. The conventional method used to calibrate and validate hydrological models involve using sediment and streamflow data from a station to obtain the optimum values of model parameters. And but in the recent year, with the vast amount of freely available data, such as evapotranspiration and soil moisture remotely sensed product, the modelers it's present a great opportunity for modelers to improve the simulation performance, especially when simulating other components, other water cycle components such as evapotranspiration and soil moisture. We can also use what we call soft data, such as evapotranspiration ratio, general data about the study area, to further improve the simulation quality and the model performance. The output variable is generated by model used two type in calibration validation: split sample test and proxy Bayesian test. In the split sample test, we have the simulation period is divided in two parts. The first part is used for calibration, while the second part is used to verify the accuracy of our model. In the proxy Bayesian test, the model is calibrated and validated using multiple sites, which can be in the same basin or in different basins with similar characteristics. Hydrological modeling often involve using a single site, typically a station or a gauge at the outlet of the watershed, relying on a single variable, which is often stream flow. Recently, there has been an increase in recommendation from the scientific and modeling community to parameterize process-based models by using multi-objective calibration. That means we can use data in different sites and with different criteria and different variables to improve the simulations, the performance of models. As you might know, SWAT plus or SWAT model has a complex structure and many parameters. In such model, two challenges or problems are faced. The equifinality problem, which is multiple sets of parameters that can yield exactly the same result for a given model. It's introduced uncertainty in determining the effective parameters during calibration. The second problem or risk is over-parameterization, which occur when a model, hydrological model, include more parameters that can be reliably estimated or constrained by available calibration data, which lead to an overfitting and a deterioration in model prediction. To verify the accuracy of our hydrological model, the next step is to assess the reliability of the model predictions. It's involve using or running a model using parameters that were determined during the calibration process and comparing the predictions to observed data not used in the calibration. To assess the performance criteria or the capacity and the accuracy of the applied and tested model, we have both statistical and graphical method are needed. For the statistical criteria, we distinguish like two types. The first type is to assess the Nash, for example, NSE and coefficient of correlation or coefficient of determination are widely used in hydrological modeling to assess the degree of fit and match between simulated and observed variables, with values close to 1 indicating a great match. The second type of statistics are errors criteria, such as root mean square error, percent bias, and mean error are usually used for errors quantification in variable values. Now, in the second part of this presentation, we are going together to run SWAT plus model by performing sensitivity analysis and manual and automatic calibration using SWAT plus toolbox based on robot data. Here are some useful links. SWAT plus toolbox guideline, and if you have faced like a problem or error, you can ask here in the SWAT plus user group, and you get some help. Just before proceed in the SWAT Plus toolbox, I would like to mention that there are other tools or some tools to be used for the same purpose for calibration and validation of the SWAT Plus model, such as SWAT Plus Cap, but each commercial product require license. And if you are familiar with R programming language, you can use R SWAT, which provide an interface for performance, sensitivity analysis, and calibration, validation, and visualization. In this presentation, I choose SWAT Plus Toolbox because it's a free software that offer multiple functionalities to accommodate the needs of users. And also it's usually used and selected because it's provide or helping users in calibration and validation and making it simpler and easier. So let's now for me, I have SWAT Plus Toolbox already installed in my computer. So I'm going just to go ahead and to open it. By double clicking on the SWAT Plus Toolbox icon. As you can see here, we have the SWAT Plus Toolbox interface in the home section. So the first thing to do is to create or to open our project. We have two options. If we have already created our project, we need just to open it from here, from this recent project section, or by clicking here on open an existing project and browse to your project's directory. In our case, I'm going to create a new project, and by choosing our text in out directory, which contain our input and output. So scenario default. So we have just to select the folder, and then we need to give it a name. For example, let's say project session 2. Save. And here we have successfully created our project. The next step is to setting up a SWAT plus model to use it for sensitivity analysis, for calibration and validation. To that end, we move to run model section. In this section, we have allow us to set the simulation period. The simulation period is by default set based on our text in out directory here in time simulation file. We try to open it, and as you see, it's the exact same time. So if you want to modify date, it's simple by just typing here in the start date and end date boxes, and we can modify, let's say 1993. There is another option. We can open the picker date and choose by clicking here to choose the month or the year. Let's choose, for example, 1992 and January 1st. Okay. Then after that, we have to give a year for SWAT model to try to understand the initial condition. And we throw entering a number in the warm-up period box. Beside we have a short period. I would type 1 year for warm-up period. And we have also to choose the routing method between Mescangum and variable storage. Let's choose the Mescangum method, the widely used routing method, as a transfer function. We have also to choose a potential evapotranspiration method to estimate the evapotranspiration. We have here like 3 methods, and we can import our file if in case we have the potential evapotranspiration data. I prefer to select the physical based method, Penman Montage, which is based on include and taking into account climate variables such as solar radiation, temperature, precipitation. Once we have selected the simulation period and choose the routing and potential evapotranspiration method, the next step is to choose the results that I want to have printed by checking the checkboxes for branch objects and for time steps. We have, as you can see, like 4 branch object components or categories. We have model component, water balance, nutrient balance, and plant and time step. For me, I do recommend to choose or to check boxes based on modeling objective, but also on our observations. Let's see what we have as observations. We have observed flow. We have observed flow at January. It's the monthly time step. So we have monthly stream flow data. For that reason, I have, or we would like to check monthly, because we have monthly stream flow data, and we know the stream flow is estimated at channel level. I won't check the yearly time step, but I want to check just the monthly for channel and average for model component and water balance. It can be used as soft data to check in model check section, to check our model to see if there are potential errors or not. So now I think we are ready to run a simulation with the current setup or setting. To do that, we just to click here on the play button to run SWAT Plus with current setting. As you can see here, we have the progress section, and we can see and visualize the simulation progress. This one with gray color is the warm-up period, and it won't be included in SWAT computation, SWAT simulation. And each box is 1 year. And our simulation is almost finished. Okay, we have successfully run our SWAT model in SWAT Plus toolbox. The next step is to choose parameters to add. Here we have parameter grouped according to different group. We have to add a parameter. We need to choose which group and which parameter. Let's select, for example, all. By selecting all, we'll display the all available SWAT model parameters. As you can see, 100 number of parameters. For either for sensitivity analysis or calibration, it's like quite impossible to use this large number of parameters for the sensitivity analysis or calibration. As we have seen before in the presentation, using large number of parameters can introduce errors and uncertainty in our model, especially the equifinality and the over-parameterization risk. And as you may know, SWAT can be used in different aspects for water quality modeling, for hydrological modeling, for erosion estimation. And what I do recommend to do is to choose to effectively run the sensitivity analysis or calibration is to rely on the user experience, but also the literature. Because, for example, in our case, we are simulating the stream flow at the outlet of Robert watershed. Based on the literature, we know that like we have 30 parameter known to be sensitive and impact stream flow simulation. So for me, I want to add just 3 parameters in this exercise to show you the change tape. When we add a parameter, let's say in curve number 2, we need to choose which change type. We have like 3 options: percentage, relative value, and replace. The first options are quite similar, because percentage and relative value change type both increase or decrease the current value by a percent for percentage change type, and by a specified value for relative value. But the third option, replace, we have to pay attention when choosing this option, because by clicking replace, we will replace the old value by a recent value, and for the whole watershed. With this method, we will lose the spatial variability of our parameter. And we will give, for example, curve number 2. If we choose replace and put, for example, a value, we will get a single value for the all of curve number for the all watershed, and that's mean the curve number, we have the same value of curve number 2 for different land use, for example, for agriculture and water. So we have to pay attention when using this option. I will add the 3 options. For CN, I prefer to choose change percentage as change type. Let's put 20 to 40. This is the minimum and maximum. By clicking here, we add our parameters table. I know also, based on the literature and my experience, that water storage available water storage is among sensitive parameter when it's come to simulate stream flow. I want to choose relative value, replace by, for example, let's say minus 0.4 to 0.4, and click on the plus button to add to the parameter. Okay, and we can add the ISCO. Here I want to get no matter to get the uniform value, one value for the all watershed or the study area. So I'm going to choose replace, and here we have the minimum and maximum. Let's choose, for example, 0.9 and 0.98. Okay, we click here, add. If you want to get further information and details about each added parameter, just click here and you get in the description panel, and here information. For example, the curve number 2 is the CS curve number is a function of soil's permeability, and here the range, the absolute minimum and maximum minimum, and the current value is 0. After adding the parameters, the next step is to add the observations. In the recent version of SWAT Plus Toolbox, we have a wide range of variables that can be added. We have river flow at yearly, monthly, daily, and even at sub-daily, hourly, and sub-hourly time step. We can add also evapotranspiration, precipitation, quality related variable. In our case, we have, as we said before, we saw before that we have stream flow data. So we need just to add river flow. And the river flow, we have one spatial level channel, because this vertical, this horizontal parameter is estimated at the channel level. In case, for example, we have observed data of evapotranspiration, we can simulate evapotranspiration and at all available level at HRU, landscape unit, or basin. But in our case, we have just the river flow at the channel level and monthly, and we have to choose monthly. For the channel number, here also we have to pay attention, because when selecting and entering the channel number, let's switch to show map. The channel number, we need to add the exact number where we have our observation. In our case, for the Robert watershed, I know that our gauge or stream gauge, it's located in the downstream part of the watershed at the outlet. For that, we can, by clicking here, we can know the channel number. But for me, I prefer to use, for more precision, I prefer to use QGIS, our QGIS project in QGIS, to select and to make sure that I choose the correct channel number. For example, if we are calibrating our model by using multi-site, and we have stream flow here, stream gauge here, we have observed data in this region, in this stream, we need just to click here and to get the channel number. And then we type 9. But as I said before, in our case, our stream gauge is located at the outlet part of the watershed. Then the next step is to import and select our streamflow file. And keep in mind that SWAT Plus Toolbox import just observation file with CSV format. We can take a look here. It's a CSV file. And for monthly, for example, at monthly time step, if we have monthly stream flow data, we have two columns, the first for date and the second one for stream flow values. And the first row, it's not read, and it's usually used as a header. In case we don't have data, we have a missing data, for example, here, we need just to put minus 99 or minus 9999. Normally, we need just to use minus 999. Okay, don't save. And we click here to import our observed monthly stream flow data. Okay, we need just to click here to import our observation file, and quickly you can see here the hydrograph, our hydrograph, the plot of our hydrograph, and some basic and descriptive statistic like the minimum, average, and the maximum. Once we have selected our parameters and observation, we add our observation data. The next step is to run the sensitivity analysis. For the sensitivity analysis, we have like 4 methods. This method For example, Fourier amplitude and Subur are widely used in hydrological modeling because they work well in non-linear processes, and it's the case when in complex watershed. We can choose, for example, let's choose this one, select this one, and put just, for example, 3 or 4. For seed, we have like 4 iteration, and by clicking on the play button, we run the sensitivity analysis. Okay. I want just to mention that in case we have several observations file, here we have to select which one or which variable we want to check or to identify the most sensitive parameter for. And also, we have when our simulation, after the simulation finish complete, we have to click here in the first order sensitivity to classify and sort our parameters from the most sensitive to the less sensitive. And in case, for example, we have this SQ, it's a non-sensitive parameter based on our sensitivity analysis results, we go back just to parameter section, and by clicking here, we remove the parameter, and we have to keep just the sensitive parameter that impact our stream flow simulations. Another thing we can see and check the progress of our simulation, either in calibration or in sensitivity analysis or in running SWAT in general. We can see the progress here in the run model section. So we still the last run, and here you can see the time for the sensitivity analysis test get and the statue. It's still running, as you can see here. Okay, I think it's okay. Okay, we need one more iteration to end the sensitivity analysis, and this is just an exercise, but in case we are looking to calibrate and validate our model, we have to select a large number of parameters. As I said before, in the hydrological aspect, we have between 25 to 35 parameters known to be and found to be sensitive in hydrological modeling, and when we want to reproduce the hydrological behavior of our watershed. But we said it's just an exercise, and we don't have enough time. I choose just 3 parameters to show you the change with the 3 different change type. Here, normally, with a large number of seed and iteration, we get different values for parameters according to their sensitivity. By clicking here, for example, as I said before, from the most sensitive to the less sensitive, and here from the less sensitive to the most sensitive. The next step. Now at this stage, I know my sensitive parameter. The next step is to calibrate and to calibrate the model with the sensitive parameters. I have like two options. I have, as we said in the presentation, we can calibrate manually or automatically. For the manual calibration, we're in SWAT Plus toolbox. We can in the calibration section, we can run our SWAT Plus model with current parameter. We can modify by trial and error and try to calibrate manually our model. For example, by just double-clicking on the parameter value. For example, is for example curve number 2. Let's write. But before I can visualize my streamflow simulated and observed hydrographs, as you can see here, in SWAT, in manual calibration section, we can modify parameters. We can compute or get statistical performance or performance criteria computed in this part of the calibration section, but also we can visualize the output result, the simulated and observed stream flow. Let's change this value. For example, as you can see here, we can analyze our stream flow or our hydrographs based on the peak flows and in terms of shape. For example, here we can see clearly that our model tend to underestimate the second peak and overestimate the first peak. Let's put here, for example, value 2 and run SWAT Plus. And as I said before, we can see here, check the progress, the simulation progress. Here we have, based on the user experience, I know that the more we have the higher value of Cn, we have the model tend to have a higher peaks. So we put like 2 and we will see the simulation. Okay. 2. Okay, now our simulation is completed. We have to click here on the refresh model performance to get the new statistical criteria. As you see, we improve our Nash criterion just by adding we can click here. As you can see, let's put here, for example, 5 and run again. So for calibration or in the manual calibration method, we just modify manually the parameter values based on repeated testing and observation until the desired performance is achieved. So usually I start by trying to calibrate manually the most sensitive parameter and then the less sensitive parameter. But with a large number of calibrated parameter, it's time consuming. And if we have like parameter dependence, it's difficult to calibrate our model manually. We can refresh the model performance. Oh, okay, that's good. So we improve, as you can see. Okay. But in case we have several parameters, I would prefer to switch to and perform an automatic calibration. As you can see, it's quite similar. There are small differences between the manual and automatic sections. Here we have an calibration algorithm. Let's put like that. Okay, calibration algorithm. For the moment, in SWAT Plus Toolbox, we have just one calibration algorithm. Let's start before the calibration. To run calibration, we need at least 10 iterations. As you can see here, equal or superior to 10. Maximize and start. Okay. We have 10 iteration. For the calibration algorithm, we have just one calibration algorithm in SWAT Plus Toolbox in this version. And in case we have several observations, such as evapotranspiration or sediment data and stream flow at different sites, we need to select here. We have different options. We select, for example, evapotranspiration or stream flow or sediment, or we can run the calibration at the same time using multi-site calibration or multi-objective variable. Another important thing to keep in mind is when choosing the objective function. As I said in the presentation, we have like two type of performance criteria. We have MASH, we have parameters that that allow us to verify or the model performance in terms of fitting and matching between the observed and simulated stream flow or hydrographs. But also we have errors performance criteria related to errors, such as root mean square error and p-bias. So here in this case, for example, by choosing coefficient of correlation or coefficient of determination. By the way, we don't have the coefficient of correlation, this option here in this version of SWAT Plus Toolbox, but in case we have NASH or coefficient of determination or coefficient of correlation, we have allowed us to assess the fit and the degree of fit and match between the observed and simulated. So the objective is, or the direction is, to maximize this fit. But when using errors performance criteria such as root mean square error, we need to choose here minimize, because we want to minimize errors. That's why we have to pay attention according to the selected objective function. We have to choose the direction either by maximizing or minimizing. What else? Here we have, by clicking here, you will see the each iteration, the calibration algorithm give a number or a value for parameter for each of the three parameters. Here we can see the variation of each parameter. The curve number 2, the available water capacity, and the ISCO. By clicking here, we can see the evolution of our NASH value. We see here that we don't have a significant improvement, increase or decrease in okay, here we have, like, we start with 0.62 to 63. But here with a large number of iteration and more other parameters that may be sensitive for and impact the stream flow in the Robit watershed, I'm sure we will get a high value of our objective function. For the validation, after the desired performance in calibration is achieved, we will take the optimized or optimum values obtained for the calibrated parameter and type them in the values. In here, for example, if I have 15 as the optimum values for CN and 0.07 as the optimum values of available water capacity and 0.09, I need just to copy and paste this value here in value and run and move and go back to the run model. As we said in the presentation, for the validation period, for the validation, we have to validate and to verify the accuracy of our model. We need just to select a new or the second subset, a new period. For example, from 1997 to 2001, and run the model without any calibration, without any modifying of the parameter, with the optimum parameter values obtained for the best simulation. Okay, here I think, okay, we have ameliorated our NASH value, as you can see, and I would suggest to run at least 500 iteration. For me, I prefer to start, especially when we have a large number of calibrated parameters, I prefer to start with automatic calibration, and then I improve manually with manual calibration by trial and error. I try to improve the simulation, my simulation. I think here we are in, it's the last iteration. We can visualize our, you can see here that our model, let's say, correctly simulate the shape file, the shape of our hydrograph for the 3 peaks, except this one. In term, and even for the peak flow, as we can see for the 3 hydrographs, we have satisfactory performance. But this one, maybe we have a problem in precipitation, or we need to add further data, or to take into account the spatial variability of precipitation, because this kind of problems, it's usually because we don't have enough rain gauges to take the spatial variability of precipitation. And as I said before, by adding like soft data or other data such as evapotranspiration and soil moisture, we can improve and ameliorate our simulation result. We click here. This is the best. So for validation, we need just to copy and paste this value here and to run the validation, to run the model for a new period. Then, as it was explained in the first session, here we can get in model check section, we can get, by clicking here refresh, we can get an overview. Beside trying to simulate the hydrological behavior of watershed, I checked just the boxes corresponding to the hydrology aspect here, 0. Okay, don't have. I have like here the precipitation, the estimation potential evapotranspiration, the curve number. I think it's quite high value of curve number, because most the higher curve number we have, the we how to say favorize the surface runoff. And for sure, for example, here in overview, probably we'll get some warning errors such as, yeah, surface runoff may be too high, because we have, as you can see here, a highest value of curve number, and we know the maximum value of curve number is like 100 or 98. One more thing I want to mention is, if you want to export your simulation results, in our case it's a river flow, the channel, monthly, or for monthly, because we run simulation at monthly time step, we can export, so you can export our simulated results at monthly time step or yearly. But if we have, for example, sub-daily, we can export our data at daily, monthly, and yearly. And we put here the channel number, if you remember, 1. And we export our result. It's a new option in the recent version of SWAT Plus Toolbox. And here we can get, as you can see here, the simulated values of stream flow, monthly stream flow. And you can use it to compute, for example, other statistical performance, because we have like more than 20 statistical criteria to use in hydrological modeling. I would recommend to use, if you are familiar with I think this one, HydroCurve package, with our programming language, to use this package to compute more statistical criteria such as KGOE and coefficient of correlation. It's just a one-line command, and we compute like 20 static. And also, you can use this file to have good like hydrographs for visualization by using ggplot in R or matplotlib in Python. And I think it's enough for this presentation. And if you have any question, don't hesitate to contact me and also contact our team. And thank you very much for your attention.
Thank you very much, Ismail. I think we reach 11:30. So unless they are very, very burning questions, what I will do is to have I will call for a 15 minutes break, and then we start again at 11:45. We are just a little bit late, and then we will have like a question and answer session later on. Is this fine with you? So
Okay.
we see each other at around 11:45 with the third presentation. I'm now going to stop the recording and start a new one later on. Thank you.
Okay, thank you.